Okay, we're talking about Lewis theory. Now we're going to look at covalent bonds. So in Lewis theory, with molecular compounds, we don't have ions forming. Molecular compounds have covalent bonds. Covalent bonds involve the sharing of valence electrons. So Lewis structure shows a molecular compound as neighboring atoms that are sharing their electrons, and they're doing that in order to get an octet of electrons, of valence electrons, or for hydrogen, a duet. So let's look at water and chlorine, and we'll draw the Lewis structures and see how that works. So let me get back to regular colors here. So for water, we've got 2 hydrogens and an oxygen. We'll learn in a few minutes how we decide to put those together, but I've done this before. Oops. So I know that the oxygen goes in the middle. So put the oxygen in the middle and a hydrogen on both sides. And we need to know how many valence electrons these atoms have. And that's easy because we look at the periodic table and the group number, 1A, 2A, 3A, tells us how many valence electrons. So, hydrogen, how many valence electrons? 1. So each hydrogen has 1 valence electron. How many valence electrons does oxygen have? 6. So I'll put 6 dots. Now, none of those atoms have octets of electrons, right? And they're not going to form ions because they're both nonmetals. And so oxygen's trying to get hydrogen to give it an electron, and it won't. And hydrogen's trying to get oxygen to give him an electron, and it won't. And so what do? Well, you have to share. So hydrogen is going to share its 1 electron with oxygen, and oxygen's going to share 1 of its electrons with hydrogen. And so what I've done here is I've drawn a line between those 2 dots representing that they're being shared. And then over here, this hydrogen's going to share 1 electron with the oxygen shares 1 with the hydrogen. And it's all very nice and friendly. When you share something with someone else, then it belongs to both of you, right? So these shared electrons belong to hydrogen and they belong to oxygen. So if we look at hydrogen now, hydrogen can count both of the shared electrons as belonging to itself. So now hydrogen has 2 valence electrons. That's a duet. Hydrogen's a little guy. He doesn't even aspire to 8. He just wants the 2 electrons. So the hydrogen's happy. Hydrogen over here is in the same situation, also happy with 2 electrons. The oxygen now has 2, 4, 6, 8, because it gets to count all of the shared electrons as well. And so the oxygen has 8 valence electrons. Do you see how that works? So by sharing, you make stuff go farther. I'm going to get rid of those circles because I'm going to do something with that later, and the circles are going to get in the way. Okay, let's look at chlorine, Cl2. How many valence electrons does a chlorine atom have? 7, right? So we'll put 7 dots, 1, 2, 3, 4, 5, 6, 7. And over here for this one, trying to do top and bottom, right and left. Exactly where you put the unpaired one doesn't matter, but I know what I'm going to do with these, and so that's why I drew it that way. So each chlorine atom is trying to do something to get 8 electrons. Now if it was with sodium, sodium's willing to give up an electron, and we'd have ions and an ionic bond. We've got 2 chlorine atoms, neither one is willing to give up an electron. So we have to have sharing. So each chlorine atom is going to share 1 electron with the other chlorine atom. Shared electrons count for both atoms. So this chlorine can count 8 valence electrons, and the other chlorine can count 8 valence electrons. Okay? Any questions about that? Again, I don't want those circles in there. So then this says identify bonding pairs and lone pairs, or non-bonding electrons. And it's important that we learn how to identify these for something we're going to do later. So we look at the water molecule, the Lewis structure for water, and we see that this pair of electrons is not being shared. It's not part of a bond. These two electrons are being shared between hydrogen and oxygen. Those are the two electrons that are forming a bond between the two atoms. So this is a bonding pair. Bonding pair. Are there any other bonding pairs in water? Yeah, what about this one over here? Another pair of electrons shared between two atoms. That's also a bonding pair. These electrons are not shared. They're not bonding. So we call it a non-bonding pair of electrons. Well, non-bonding is kind of long. So what we usually do is we call these lone pairs. Lone pair means the same as non-bonding electrons. This is a pair of electrons and it's just out there alone. So there's a lone pair, and then we've got this is a lone pair. So we should be able to look at the water molecule Lewis structure and say, well, there are two lone pairs and two bonding pairs in the structure. So let's do that with chlorine. So in this chlorine molecule, how many bonding pairs are there? There's one, right? It's this pair in the middle. That's the bonding pair. In the whole molecule, how many lone pairs? Not lone electrons, lone pairs. Someone was thinking 12. 12 electrons are involved, but it's 6 pairs. All right, here's a pair, and there's one, and there's one. So there's 3 lone pairs over here, and 1, 2, 3 lone pairs over there. So these guys are the lone pairs. And there's 6 of them. And the same on the other chlorine. Any questions? We'll need to be able to identify bonding and lone pairs later. So that was called a single bond. One pair of electrons is being shared. Single, one. Right? We can also have more than one pair of electrons being shared. So let's look at an oxygen molecule. So it's O2. So there's one oxygen, and here's the other oxygen. And we already covered this. Oxygen has 6 valence electrons. So we put 6 dots on that oxygen and 6 dots on this oxygen. And we're going to see how can these guys cooperate and share so that they can both have octets. Well, we'll start by sharing one electron. That's kind of crooked. So we're better now. They each count the pair. So now they each have 7 valence electrons, but that's not 8, and that's not good enough. So they're also going to share another electron. Now because of how I drew this pair ends up being down below, but that's not where it's going to be. It's going to be between the two atoms. So I'm going to leave that over there and redraw this. So we have 2 pairs of electrons. They are going to be shared. And then each of these is going to have 2 lone pairs. Okay? So this oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. Both atoms have an octet. That's why oxygen forms a diatomic molecule. That's why chlorine forms a diatomic molecule. because when they form those diatomic molecules, they're more stable because now they have 8 valence electrons. So normally, we wouldn't draw the dots with the lines between them. Normally, we would do it this way. We would have oxygen, and we just do 2 lines, and then put the lone pairs around. And it doesn't matter where you put the lone pairs. Just top, bottom, right, or left. So this is a Lewis structure for oxygen. It often helps, especially when you're beginning, to put the dots in there and connect the lines, connect the dots with a line, because that helps you to remember that each of those lines is actually 2 electrons. Whereas over here, sometimes we forget that the line is a pair of electrons, and so we count wrong. Okay, let's look at nitrogen. How many valence electrons does nitrogen have? 5, yeah. These are not trick questions here. Wake up. It's okay. 1, 2, 3, 4, 5 for that one. And 1, 2, 3, 4, 5 for that one. Now, there's a pattern here that, if you recognize it, can help you as you're doing Lewis structures. When I drew the oxygen atoms, how many unpaired electrons did it have just in the atom's Lewis structure? There were 2, right? This one and this one. And it ended up making 2 bonds. In the chlorine atoms had 1 unpaired electron in their Lewis structure. They ended up making 1 bond. How many unpaired electrons on this nitrogen atom? 3. Guess what? It's going to make 3 bonds. Those unpaired electrons are the ones that get shared. So we'll share these 2 because they're nice and close together. And that's helpful, but not enough. And so then we'll share these guys, and we'll share those. A lot of sharing going on here. The nitrogen, this one, counts the lone pair, and 2, 4, 6, plus the lone pair is 8 electrons. The other nitrogen, 2, 4, 6, 8. So, it's a little awkward. A lot of times when you're drawing Lewis structures, you're going to make a mess first, rough draft, and then copy it over. So what we really want is 3 lines. There's the nitrogens, and kind of like to make things symmetrical, so I'll stick the lone pairs on the outside. This is called a double bond because we're sharing 2 pairs, and this is called a triple bond because we're sharing 3 pairs of electrons. Any questions? A lot of this stuff, once you really see it, it's like somebody turned the light on in a dim room, and you're like, oh, is that all it is? Yeah, that's all it is. But when the light's off, it's really hard to figure it out. So hopefully we'll turn some lights on. So the Lewis model predicts that H2O would be stable and H3O would be unstable. We can also look at H2O2, which is hydrogen peroxide, and H3O plus, which is the hydronium ion, and see what the Lewis theory says about that. So we've already done water, so I'm not going to go through the whole thing again. Oops. But there's a Lewis structure for water. Each hydrogen has a duet, and the oxygen has an octet, and Lewis theory says that's good. That's going to be stable. So if we make H3O, how are we going to do that? Well, we're going to have to put another hydrogen on there, right? So here's a hydrogen. Oops, this is a fat hydrogen. I'll slim him down a little bit. Here's another hydrogen atom, and it's got 1 electron. It's going to come into this water molecule and say, hey, I want to be a part of this. What can we do? Well, oxygen could share one electron with the hydrogen. That makes the hydrogen happy, but what's up with the oxygen now? It's got 9 electrons. 2, 4, 6, 8, 9. Not cool. That's too many. Oxygen can't do that. So we look at the Lewis model, the Lewis structure for H3O, and we say that doesn't work. We can't make that satisfy the octet rule. That's probably not going to be a stable molecule. And it is not a stable molecule. So the problem with that is that the oxygen has too many electrons, right? So if we took away one electron, let's get rid of that guy. Now removing an electron from that molecule is going to result in it having a charge, right? Taking away an electron, we're going to have a +1 charge. But what does the Lewis model say about this? Is that good? Does it satisfy the octet rule? It does. The oxygen now has 2, 4, 6, 8 electrons. Oxygen's happy. Hydrogen always ends up being happy. All he needs is 1 electron. He's easy to satisfy. So we've satisfied the octet rule. Lewis theory says that's probably a stable polyatomic ion, and it is. Let's look at H2O2. Kind of have to just start again over here. So you can experiment with different ways of connecting these, but there's actually only one way you can do it. Hydrogen with 1 electron can only make 1 single bond. It can't be in the middle. We couldn't put hydrogen in here and have it bond with 2 other things. It can't do that. It can only make 1 bond. So the hydrogens have to be on the outside. And so we're going to put these 2 oxygens in here and look at the Lewis structures for each atom. Hydrogen has 1 electron, and each of the oxygens has 2 electrons. What am I saying? 2. I'm drawing 2. 6. Each oxygen has 6. And then we see, well, how can we share to get octets? Well, the oxygen can share with hydrogen, so that hydrogen's happy. This oxygen can share 1 with the other hydrogen, that hydrogen's happy. And then these oxygens can share 1 with each other. And again, we see that the oxygen had 2 unpaired electrons, and it's making 2 bonds. So here's oxygen with 2, 4, 6, 8, and this oxygen 2, 4, 6, 8. Lewis theory says that's probably a stable molecule, and it is. Any questions? I'll spare you the joke about H2O2. Covalent bonds are directional, right? They involve a pair or several pairs of electrons between 2 atoms. And if you move that atom, if you move the pair of electrons out from between, then you don't have the bond anymore. So covalent bonds are directional. Ionic bonds were not. They're just attractions between opposite charges, and they go in all directions in the crystal lattice. So covalent compounds contain discrete molecules. They are not a repeating lattice of alternating ions or even alternating atoms with covalent bonds. They're discrete molecules. So why do the discrete molecules stick together at all? Well, there are weak forces that hold the molecules together, and we're going to learn more about those later. But if you remember from 3A, that's dipole-dipole forces and London forces and hydrogen bonding. But it's not covalent bonding. Those are weak forces. And so because the molecules are held together by weak forces, molecular compounds tend to have lower melting points. So here we have an illustration. It's pentane molecules. And the pentane molecules are held together by these weak interactions. And so this will be a liquid at room temperature. Within the molecule, we have strong covalent bonds. And so those molecules stay together. As you heat them up, you can get the molecules to separate from each other, but the atoms within the molecule are going to stay together.